So now we've looked at how we can sort of like structure code into little chunks, which are tasks that get scheduled, and that we can then sort of have certain ways of controlling like the data they access or how we can sort of synchronize between them. We need to also then maybe share data between them. And this is sometimes more sort of complex than just having like this structure with a mutex that locks itself, like a shared resource, but more so sending synchronization signals that have more to them than just saying, yes, 1 or 0, I'm here or not, right? And so then we look at POSIX and like sort of what it defines as like operating system sort of standard ways of sharing data. And there's a few different ways that it defines, like namely sort of like this pipes, which I mentioned earlier, and I did an example with LS and I think with grep, where the output of one program is put into the input of the next program, and it sort of helps you to chain programs instead of processes or really share within like a free RTOS environment sort of thing. It is an IPC because each program is essentially a process, but it's a IPC used for more advanced operating systems than what we'll be looking at. So we're not going to really be looking at the same sort of thing as pipes, because our free RTOS sort of project, platform, system, whatever it is, program that you develop is one program, and so we're obviously not going to be using pipes within a single program. POSIX also defines something that are called message queues, and now so this is similar to what we'll be using, is that they are used to send sort of messages that have a fixed sort of size. I mean, in POSIX's sort of definition, they have a fixed size header, and they can have a variable length, so the text of them. But FreeRTOS is a very similar thing. They have these queues which are similar to like a pipe, and some sort of like a persistent connection that you build where you can sort of send in a structure or a predefined sort of data element in like a buffer style, right? We have semaphores, which we've previously mentioned for synchronization. So this is sort of very much a binary signal, as well as shared memory. And this is what I mean by this should be. I mean, you don't have to. You can use shared memory without locking it, but then you're also running the extremely large risk that your program's going to crash extremely quickly or do things you don't want to. So shared memory should be obviously locked and used in a multi-threading friendly way. So then, looking at the FreeRTOS IPC and what they expose and define, we can have these stream buffers. And so these are similar to POSIX pipes. They stream from one task to another instead of one program to another. They have a single writer and a single reader. So it's really that you're building a connection between two endpoints. Now, we won't really look at these and we won't use these, but they're a very similar idea to a pipe. So it's a streaming of information between two fixed points in two different tasks. Now, one thing we will use a lot of, and are very common, and also they're actually the basis of a lot of other FreeRTOS functionality, such as semaphores, is queues. Now, queues are generally like a first in, first out buffer. So, you push in one end and they come out this other end in the order that they will put in. And they're a way of sending messages between tasks. And so they can also be used for interrupts, but really they're just used for sending packets of information in some sort of predefined way. You're saying, hey, I'm sending integers, and you're going to keep sending integers through this pipe from one task to another. And they have the functionality that the tasks can block on them, meaning like tasks that are waiting for input, they can block until the queue has something to send it, and then they can process it. So they're very much useful for sort of, as you can imagine, some sort of like data processing pipeline that the tasks will sort of wake up, do their thing, send the data on to the next task, and then it will in turn wake up and do its thing. And so they have this sort of ability, and they're also very flexible in how they send data. And you can also, for instance, you're not also forced to use them as a first in, first out buffer, but they generally use as first out, but you can configure them to be used however you want. You can also manually write to the front of the queues. They're very flexible, thing within FreeRTOS. So anyway, then we have these semaphores, which we mentioned, and shared memory. So this should be locked, right? So streams, we'll sort of skip this. And now if we look at we'll sort of skip this again. So now we'll look at queues. Now queues are an extremely important one. So the data it sends, an important detail about queues is that the messages sent are done by copying data. And so this, if we remember back to the C programming lectures when we talked about pointers, a pointer, if you were to put a pointer into memory and send it, the other task would be accessing the same location in memory, right? It would dereference the pointer and it will go to the same address. And if both tasks had a reference to the same memory address, nothing's to stop them. I mean, unless you're locking it, nothing is stopping them from from accessing the same memory address. So therefore, sending if a memory address through a queue sort of defeats the purpose. If you want to use a memory address, a pointer, then just put a lock on it and make sure that you use locked, like a shared resource side of style IPC. So a queue is really used for sending data, and therefore we send by copy. So that the data that's put into the queue is not the data that was used in the function where it was put in. Because if you remember the scope of the function, the data that is inside of the function, if it was put directly into the queue by reference, when it arrived at the other side, the task might be referencing the data created on the stack of the other function, which maybe the function returned and it's no longer valid, and then we get into sort of memory issues. So to avoid these problems, queues work on copying data. Similar to when I was talking about how we have the mutexes to lock structures, and a really good way of returning the values of the structures to create copies of them, queues do very much the same thing. They avoid memory or memory access errors by creating copies of data. And so the data is copied into the queue and it's then copied out of the queue, right? So this is what we have here. Now, there's a few other advantages to them, namely that you don't have to create buffers. You create a queue and it inherently creates the buffer for you. And so then, because as well of this copy in, you can have in your sending function one variable that is constantly updated, and every time you want to send the variable, you just put it into the queue and it's copied into the queue, but then you can then reuse that same variable, meaning that you can have a very low memory footprint on your sending task or on your receiving task, in that you only need to really keep one copy of the element that the queue actually sends and receives instead of having an array of them. You know? And this element that you're sending can be whatever you want. It can be a raw chunk of memory. I mean, you define the size of it really by telling it how many bytes this element's going to be, and it's up to the programmer then to access this element when they receive it. Because really, you just get the whatever was in the queue copied into some variable that you've created, and it's up to you what's actually, how it's structured and whatnot, right? So we'll look at the API quickly, or we'll look at sort of how we can synchronize tasks between it, right? And so the useful thing is that tasks can block on this queue, as I was quickly mentioning before, right? And so this is really useful in that when we have this progression of like the data needs to get processed between multiple tasks, or the tasks have dependencies on this data, we can then make sure that they're synchronized explicitly through using queues. We don't need to actually use a semaphore on top of it, because that would maybe be a bit of overkill, right? So let's see if there's anything else. Yeah. So looking at the API, it's really quite simple. So we have a create function, and similar to the semaphores and the tasks, the queue API uses handles. So we have a queue handle that is used to reference the queue. Now the queue itself is created of a certain length. So if we look at this thing here, we can see here we have a queue of length 7, and it has 7 of its elements. And here, for instance, 2 of them are populated. So we're saying here we have a length and with the size of each individual message, right? So this is a structure that you've created. You could use a size of operator to give you the amount of bytes you need, size of int, whatever have you. Like this is the size of operator will probably come in handy here. Similarly to an init, we have a dinit. So this is if you want to like sort of kill the queue, you don't even, no longer need it, then you use the dinit. Now there's a number of different sends. We can either just send to the queue, and so if the queue is configured to be a first in, first out, this will push it into the back of the queue, but obviously we wouldn't, meaning it would be the last one to be read out from what's already existing in the queue. Very much the same as send to back, right? Now, but the send to back is sort of explicit in the sending it to the back. The queue itself depends on the sort of the queue that you've created, the policy or the sort of buffer that you've created, whereas this one is explicitly sending it to the back, same as that this queue send is explicitly sending it to the front. So we'll put it at the front of the queue. So if it's a FIFO queue, this means that it will become the next value to be read out. And this can be very useful if you want to, for instance, make sure that the most recent value is put at the front of the queue. Similarly, opposite to the sending, we have the receive functions. Now they come in two sort of styles. There's the receive, and I was mentioning that the queues do a copy on receive. Now, the queue receive copies the object out of the queue and then removes it from the queue. So it means that like if the queue had only one object in it, it would then become empty. So this is, for a lot of reasons, good. If you're sending or processing like network packets, you would then only have one copy of the packet. You don't want to accidentally create multiple of the same packets, which means that you've sort of created data that was never really needed. And this is probably, for most networking applications, not really ideal. So that's the receive, is that it copies and sort of destroys what was in the queue. Now the peaking is slightly different. It takes a copy of it, but it doesn't destroy it from the queue. And so this can be really handy if you want to sort of ensure that there's a copy of data always in the queue. And so my students have found really creative ways of using queues for sending, for instance, button presses on a game controller. They always want to make sure that there is some information in their queues, and so they will create a queue of length 1, so that they always only have one, like the most up-to-date values. Then there's also a send or a queue overwrite function, which will actually force overwrite anything that's in the queue. So meaning that they'll update the queue with the most recent one, but they never receive from the queue, they only ever peek into it. So that there's guaranteed to always be some data in the queue, right? And so this way they can make sure they can use a queue essentially to create a memory safe, shareable sort of reference to the most recent data of something. Namely, they use it generally for button pushes. So when I saw that was a really creative use of them, I was very impressed. So similarly to the other like semaphore and mutex sort of gets and takes and gives, or mostly just the takes, we also have block times, as we can see here. So this means that if some other task is currently reading from the queue and the queue is not accessible, or some task is writing into the queue, then another task might block on it. And so therefore we have to specify how long to block for. Now you can see here, for instance, the send and the receive, they take, here it's explicitly said reference, and here I'm talking about a buffer. So this is also a reference. Now, as I don't want people to get confused and saying, hey, you're saying it copies them, we don't want to put pointers. But so the queues API requires you to put in the memory address, the pointer, to where the data should be copied into, right? So actually, when you're sending, you create your local variable in your function scope, and then you're passing a reference to it, and then inside the queue send function, it will copy that memory from whatever's at that memory address into the queue itself, right? So you do have to make sure you use the right references and pointers here. But we'll see that in an example in a second. So an example of using it, this is actually from the free RTOS simulator, or I think it's now called the emulator, in that we have the button presses from the keyboard that are sent to the user using a queue, right? And so how they're actually sent is that I send a lookup table where the states of all the button presses are in there, right? But each individual element in the queue is an entire lookup table. And so we define the queue here using a queue handle. In this case, it's an external, meaning it can be used in other C files. And so we have the import queue, this is the name of it. And so for instance, here's a small version of the lookup table where each character of the possible button presses on your keyboard is this unsigned character where it's either 1 for it's yes, it's been pressed, or 0 for no, it's not being pressed. And so what we can do is in this init function where this queue is actually initialized, we essentially set the handler to the returning result of this execute create. So what I'm doing here is I'm creating a queue of length 1, and I'm saying, hey, every item in my queue needs to be size of buttons t, and this is my structure here, this type def structure, right? So then creating a task here which is separate to it, and all that's happening in this task though is that I'm overwriting it. So this is actually me where I'm using the same implementation as what I mentioned my students use, in that I'm constantly writing to this queue of length 1 the most recent values of my buttons. And so here I'm referencing the queue that I want to put it into by sending in the handler, and I'm putting in a reference to my button structure that is stored within the scope of this C file, right? So on the other end, like somewhere else, in here, this is being done in the back-end libraries of this simulator where I'm sort of updating this queue with this most recent values. But then in the sort of the user's code, where like you would write your code and you actually want to get the button presses, you can use, for instance, QPeek. You could use QReceive, but then obviously you run the risk that the queue is empty and you can't get any more information, which could be useful. I mean, there's not a stupid, there are definitely lots of cases when this would be useful. But if you were to use QPeek, meaning that you copy but don't remove it from the queue, then you'd have to sort of reference the queue you want, put in a pointer, in this case this is passed to this function, where it should be stored, so where you should make a copy of this whole like button table, and then also the block time. So what this means is essentially this QPeek call doesn't want to block. So it's either going to populate the table or it's not, and it's just going to move on. And therefore buttons here would not be populated, probably have a value of null, right? So then we get on to an IPC that is very much FreeRTOS specific. And this is something that FreeRTOS created. And what it is essentially it's a semaphore and a message queue, where the semaphore is used that you can sort of give and take it. And you can block on it, and you can use it to wake up tasks. It functions very much the same as the semaphore, but the idea is that the semaphore actually has a 32-bit value associated with it. So it's not just a binary 1 or a 0 like a semaphore, but it has these 32 bits of information. And so if you think about it, for instance, if you're setting flags, like binary bit flags, then this is 32 flags that you can send, which can store a lot of information. And so 32 bits can be used to send a fair bit of information, and for a lot of situations it's actually more than enough for a lot of basic applications. And so the thing is that the task notifications are actually extremely fast. They're very well implemented on FreeRTOS, and for instance, if you were going to use a semaphore, you should probably use a task notification because their overhead is actually less. So there are a whole different sort of ways that you can set or send the task notification, in that you can set the task notification. So like when you wake up the task, it has its notification value set. You can sort of overwrite it, or you can set without overwriting. So this is logical OR. You can force overwrite it. So this would be a logical AND. You can set it a bitwise mask. So this is a logical masked OR, or you can just increment it. Right? So it's sort of like making it into a counting semaphore, right? And so exactly, they use for sort of synchronization by sending small amounts of data, and they're actually extremely fast. So this is very much a FreeRTOS characteristic, and the API to use them is more or less the same as the semaphore. The only difference is that what you actually essentially you give, you have the option of using the notify without the give, so the xtask notify, and actually putting in a notification value. If you use this xtask notify give here, then you're using it very much in the exact same functionality as a semaphore. And the take here also has the option of you passing in a notification value, so that when you actually wake up because you're blocked on it, it will set or it will clear the notification value based on what you put in here, right? So here are the different actions that you can have, right? This is the flags that you go into here to tell it which one or how the notification value should be handled. Because then we can look at the sort of the overview of the IPCs that are available in FreeRTOS that we'll be using or being exposed to, and sort of like how their complexity but also sort of their speed, right, goes. Because task notifications, these are like sort of like the lightweight and the quickest, and the more advanced and more sort of excess functionalities we bring in becomes more complexity and more overhead as a result, and therefore less performance. So mutex is because they have to do this whole priority inheritance thing. They're extremely secure and they protect against priority inversion, but they do have a lot of overhead, and so they have a pretty harsh performance. Minus compared to some other things, but I mean you can't, for instance, implement proper shared resources using a binary semaphore. Then you're opening yourself up to priority inheritance or priority inversion. So here's a quick summary of them. So I think now, before I get into software timers, I will do a quick example of these.